society. So, um, the last conference that I was able to speak at, I was able to introduce the McGinty equation, or the MEQ as I call it, which is a novel method of combining quantum field theory, fractal geometry, and gravity together. So it creates this unified framework that I've been exploring more and more as time has gone on. Where I've focused my attention to begin with, and especially over the last, say, few months, has been on quantum computing and errors. This honestly is low-hanging fruit for this equation. And so what I'm trying to do is get the quantum computing error mitigation explored more so that we can solve those problems right away. Because once those problems are solved, the quantum computing, once it's reliable and it can be more practical, it will just explode as far as what we can do in terms of artificial intelligence and other types of groundbreaking advancements. So really, where I'm seeing the industries going are for the quantum computing and quantum sensing are really two of the most rapidly advancing fields that are leveraging different unique properties of quantum systems. So quantum computing, what it's trying to do is to outperform classical computers kind of exponentially in basic computational tasks, while quantum sensing is striving more for an unprecedented kind of precision and measurement. But both of these, the quantum computing and quantum sensing, have significant challenges due to the inherent fragility of quantum systems in general. So what we're taking a look at is error mitigation. And it really is something that's crucial. The major quantum computing manufacturers, Google, IonQ, there's quite a few. Meta is now working on some of these things as well. Microsoft, of course. The current approaches are using some more error correction codes, and then there's error transparent gates, which they don't really necessarily get all of the noise, and they only are really for specific types of noise. So the equation that I have would actually combines that and gets to a different level. So we do have some basic techniques that have some limited scope right now. Again, the QEC codes and dynamic decoupling are really only for some specific noise processes. So the MEQ framework, which combines quantum field theory, fractal geometry, and gravity, does combine and incorporates both quantum and classical effects so that you have more of a systematic analysis of what's going on. And what's really exciting about it is actually the fractal potential term within the equation gets in and gets some complex noise processes that are not addressed at all right now. So there's really some interesting advancements that will come with that. So just to kind of recap when I talk about MEQ and why I'm calling it the unified equation of physics, is because this equation, in fact, does unify general relativity with quantum mechanics. So you basically start with the Schrodinger equation, and you add a fractal potential term in there as well, and right in here, and then we can add the gravity as well too. So this is this is the simplified form of it, and there's much more complex forms of this as well. But what this will do is it gives us a unification of the theories, the quantum field theory, the fractal, and the gravity, which gives us the ability to make very, very accurate testable predictions, and gives us some really interesting different type of applications with it. And these applications are in magnitudes of order higher with quantum computing without error. For example, IonQ right now, they've got 11 qubits that they can use, or 11 qubits that they're the trapped ions that they're having, but they're really only able to use about 8 because of the decoherence and the gates on there. Adding even one more of those just really expands the power, the computational power of the quantum systems. So that's part of the idea. And the other thing too is that we're really looking to have as few qubits as possible. It's a similar type of situation with AI where if you had 100 qubits, granted, it seems like mathematically you'd have a lot of computational things you can do with, but at this point in the stage, there's really nothing that is going to use all those. If you had 6 qubits that were all working perfectly, you would have a better working computer or computational system. Similar to ChatGPT 3.5, in many cases, it's a lot better than ChatGPT 4 or some of the other ones as well too, because it's a smaller scale model and has different learning things. That's kind of where we're going with this. So the role in the error mitigation is this will help us understand what's really going on by taking a look at the actual perturbations of the gravity in the actual fields that are going on. This will then allow us to mitigate the errors and enhance the accuracy. So basically what we're doing, what this equation does in the simplest form that I can put it, is it measures the fractal deformation of the energy field itself, which enables for a very, very precise amount of measurement. And it also enables us to regulate the uncertainty principle, which is when you can measure a thing, you can regulate a thing, which will give us some really profound insights into that function of kind of one of the strange paradoxes of the quantum world. So we've got different strategies that we're going to be doing. There's a modified version of the equation, which I'm going to be introducing today as we talk about how to go about and do different techniques. We're actually going to really kind of come full circle and come to a hybrid solution that uses both QEC classical methods, because those are very good and work well at the macro level. However, the MEQ takes it very, very deep at the micro level and handles some of the things that are these pressing problems that we don't have an ability to take care of right now. So what we're going to do is we'll have, again, better why we're doing this, better predictions, better sensing, and we want new technologies that are come out of this. There's some really fascinating technologies that are going to be coming our way because of this. So in order to really understand the errors, we want to do what's called an error analysis. And so we're really taking a look in using the entire equation or the entire spectrum from the micro to the macro, which is an informed closed loop as well, which I think is one of the other areas of this that's kind of revolutionary, because we'll be able to figure out what the types of errors are. We can then understand what the rates of them are, why they're happening, and then also figure out how these are propagating in the compounding circuits. So getting to this point getting this error corrected is going to be something it has to happen for us to do this. It's going to give us efficiency, and it will also boost the accuracy. So what can we do with it? One of the first things that's going to happen once we've gotten these errors taken care of is quantum cryptography. We can use the MEQ equation to encode on topologically for the non-Albion anyons, which I'll talk about a little bit. What this does is it creates a fractal way to encode as well, which basically, if you can think of it, changes the lock every single time somebody looks at it, which makes it incredibly difficult for even a quantum computer to crack the code. In the order of thousands and thousands of years for even the most advanced quantum computers of the future to be able to mathematically crack this. So what this will do is it will enable a unbreakable quantum security, data security for systems, even before we've got quantum computers that are powerful enough to crack those codes. Quantum computers will be able to crack in a matter of seconds or minutes all of the standard, conventional, classical forms of cryptography that we have. However, this enters in a completely new element by adding an almost infinite and scalable fractal potential to it, which again will be very good for all of us for privacy, and I think that the governments, and there are some cases in secure communications where you don't want eavesdropping. This system will obviously, if you observe anything in the quantum realm, it changes immediately. So there's no eavesdropping can happen. It automatically would detect if there's any other type of way or person that's looking for this information. So this is going to become a big key, and you're going to hear probably a lot more about this in the coming months. Material science is another big area. I've been using this, the equation in this area, very successfully, I think, in the terms of doing hydrogen splitting. So we're able to use some different graphenes and different other types of like C16. That's another one that's coming out now, where we can use these different materials, and we can use the MEQ equation to create a formulation of about 14 different algorithms that will then get us to a point where we believe we can make a working prototype of a spark plug that runs on water, burns the hydrogen, exhausts pure oxygen. And these would fit in, any standard vehicle. So that's a big thing that's going on. That's more at a governmental level. But material science, this is an area where we can use this equation to really go in and create new types of materials, like things that are maybe as strong as steel, but as light as air. Things that have materials that have different magnetic properties. Materials that have different, potentially in the future, even things that might even have negative mass. And so those types of things will then come into play for major technologies that are going to be coming down the road for us. Drug discovery is another big thing. The healthcare side of this and the quantum sensing and imaging is going to greatly advance our, the medical care and medical side of things. So we're going to find new ways to use these molecular simulations that will then leverage the error mitigation for very, very precise measurements and reducing the noise to then create new algorithms that will then create totally new medical technologies for people. So when I talk about quantum algorithms, this is an important function of this equation as well too. What the quantum algorithms will do is, and there are a number, an obvious one is Shor's algorithm. Many people know about that. Shor is from MIT, and it really has established kind of a foundational quantum algorithm that's out there. But these algorithms will, in fact, impact quantum machine learning and impact machine learning as well. So AI will benefit tremendously from these advancements of this equation, meaning its speed and computational power will become almost unfathomable. What we can do with these algorithms is we can then mitigate the errors, and we can use these for what they call quantum classifiers. These neural networks and quantum classifiers that I'm talking about at this point in time will go into play later for more of a fractal construction or a fractal architecture that I will get into as well. But the quantum algorithms play right into this different mathematical insights. So how we're making or building these algorithms is we are going to be using the McGinty equation to begin with. And this is basically tells you the perturbations in the gravitational effects within quantum field. And that equation does have the terms. There's a specific term within there, within the fractal potential term, it's an S. And oftentimes I've been asked before if that's spin, but that's actually scaling. And what that does is that scales out multidimensionally. So you can go out into other dimensions, other scales to find the self-similar fractal structures. And when you look at the error codes and those things from that perspective, you get new insights or different insights than you would have normally. So the fractal effects come from this V0, L, and S are the terms within the equation that would describe the fractal structure. We can then extend the MEQ with the general relativity. And this is where we really start to see some interesting implications when we add gravity into quantum mechanics. I've even had professors, esteemed, well, I wouldn't say necessarily esteemed, but very intelligent professors that are asking me, well, why does it even matter? Why would you even want to, does gravity even have any effect or have anything to do with things at this level? Which is shocking to me because gravity is, of course it does. I mean, just because we're not able to measure it at this point in time doesn't mean it's a non-element. So gravity plays quite an important role at the micro level. We can see it observationally at the macro level. We can see that the universe is expanding. This has been documented by observational evidence. So on the quantum level, things operate a little differently. But when we apply the fractal structure or the geometric framework over it for the self-similar fractal structures and the perturbations of the field, we can then start to see different types of insights that we would never not see before, that will then enable things, such as quantum internet, quantum telecommunications, and some micro wormholes. There's some really very, very fascinating things that are now going to be possible because of this. So how we want to enhance the qubit stability. This is kind of important. For example, it's not going to do any good for us to have qubits that can only go 10 feet, right? Or maybe 1,000 feet. Ooh, big deal. Well, we're going to need qubits that can go across the cosmos, right? And so I think what we're really willing to look at is how do we go about doing that? And the dynamic correction in the real-time correction is one of the things that we're kind of working on, is trying to figure out how we can extend these coherence times. And the continuous error correction, when I talked about the micro and the macro, when you combine the general relativity with the quantum fields, you end up getting a closed loop type of structure where the micro informs the macro and the macro informs the micro, which can lead to some interesting insights on all types of research, actually. So we want to incorporate the fractal geometry. I just spoke about this. We account for the perturbations, and then by correcting these perturbations, we can stabilize the qubits. So it's the first step is to find them and understand them and go from there. Where we go from this is I did want to mention that on the macroscopic level, traditional and classical quantum error correcting works very well, and in fact should be used in some of those cases. There's no one bullet for everything, if that makes sense. So what I've really been looking at is a hybrid error correction form where we actually take the traditional quantum error correction for the macro, for any of the bigger, and we use the MEQ to model for the micro parts of it. And what we can do then is by combining these error codes and the correction codes, we can address a wide range of errors. And we are going to have more robust, fault-tolerant type of pieces as well. One thing I wanted to really talk about too is there's a very interesting thing called these non-abelian anyons. And this is an important portion of this because these are a type of quasi-particle which are found in specific two-dimensional quantum systems, and they play really a significant role in fault-tolerant quantum computation. So unlike the Albion counterparts, the non-Albion anyons, they have non-commutative statistics. So what this means is that the outcome of exchanging two non-Albion anyons doesn't only depend on the order of the exchange, but also in the specific path taken during the exchange. So these provide a robustness against certain types of errors and decoherence, and that really makes them promising candidates for the implementation of the topological quantum qubits, where we can encode information topologically, which would then significantly enhance and reduce error correction and reliability. We can then take a next step further. We'll optimize the quantum algorithms. So this is going to be the next step to once we have the error correction in place. We've got optimized algorithms. We can then move into something called fractal computing, quantum fractal computing, which I'll touch base on a little bit here. Quantum repeaters is another method or another area that we're going to want to work on with this modified equation. Because we're adding that term gravity in there, we can actually start to generate higher quality entangled states. And so what that'll do is it's going to give us basically several different benefits. So you're going to have a reduction of decoherence for one. And this is kind of an important part too, is it's going to mitigate the phase and amplitude errors. Those are some of the errors right now that we don't have very good QEC for at all. And then we're going to have the fidelity for long distance entanglement, meaning we're going to need to have instantaneous communication on the other side of the planet, right? And we can do that, but we're going to need to have some other methods in there as well, because the qubits, they deteriorate so quickly. And that's why we want to use particularly robust quasi-particles for this. When we optimize the qubit allocation, this is kind of what I was talking about before, where IonQ's got 11 ions that they've got trapped, but they can only use 8. What we're going to want to do is use the different fractal dimensions that we can then reduce the number of them. If we had 6 that were working perfectly, it would be on a magnitude of, it's an amazing amount of information that could be processed quickly through superposition. So it would also decrease the number of interactions that we need, which has a scaling factor, and it lowers the error rates as well too. And again, here's another visual just to kind of explain what I'm trying to do, or how we're getting across to make things probably the most effective and efficient, based mathematically and theoretically. Of course, this still needs quite a bit of research and experimental validation, but we're on the road to that. So the first step would be to minimize the physical qubits that we need to correct for the error. So if we don't need to have 11 qubits, if we can have fewer qubits, that would be optimal. We want to use the MEQ to model the system, and then we add that fractal potential term, and then we adjust the parameters to optimize the efficiency, which means take care of those perturbations. And then we simulate the encoding schemes, and we analyze resource requirements for the local fidelity. So this whole process right here is ongoing all the time and in real time within the system. It enhances machine learning. There's some different reasons for this, obviously, not just correcting errors, but it will make the structure of the machine learning algorithms and the quantum algorithms better. What we're looking for in the future is we're going to apply the error mitigation just in general. We want to account for gravity in our measurements because it's there and it makes an effect, and it's really kind of the key to some of the new technologies that are going to be available in the quantum space. We want to have better fault tolerance, and this will lead to what we can call novel architectures. So now that we've completed some of these things, we're moving forward. Let's say we've gotten to the point where we've experimentally validated things. We can start working on building some new things. And this is where I was talking about the fractal computing. So this is where we can combine quantum computing with the complexity of fractal mathematics, which will then give us a way to scale the quantum computing out. Fractal optimization is another area that we're taking a look at just to understand how that would work within the fractal computing methods. Fractal nanomaterials are another area. This goes back to the material science where I was talking about the type of materials that we'll need in order to split hydrogen, and using solar power to split hydrogen. We can also, of course, use water to do it, but the most effective way is going to be to farm the hydrogen directly from the sun. And we can use the fractal nanomaterials to create ways to store that in ways we can't even imagine right now. Quantum encryption with fractal keys. This is what I was talking about before. This is imperative. Once quantum computing becomes not even mainstream, but once they are within an effective state, they'll be able to break and crack any encryption that we have, which could be devastating. So this is something that we're going to work on up front with some of the cybersecurity companies, just to make sure that we have some systems in place for that. The fractal resonators, this is another really interesting topic that we've been looking at. It's a way that we can actually process and solve different complex problems. It increases speed, and they use these fractal patterns that create this a really powerful computing system. So these will be some other new technologies that are going to be coming based on the error correction and the mitigation, which we're working on first. Fractal sensors, these are what's going to really revolutionize material sciences. And sorry. And then we also have, so what we're looking for moving forward is we have different hardware improvements. We want different, we're going to find new scientific discoveries as the quantum computing error mitigation comes into place. There's going to be geniuses around the world that are going to come up with things that new discoveries that are going to make us reevaluate things again. So that and the academic collaboration, I think, are the things I'm most excited about moving forward. So to summarize, the MEQ is a new method to error correct. It's compatible with the existing quantum hardware that's out there, and it's can be used to develop new hardware as well. And it does make things more practical. So it's really something that's going to be separating the different companies by the ones that are using it and the ones that aren't. So we have several different takeaways, broad applications. It's because it is a mathematical and algorithmic implementation. It can be very practical and doesn't take very long to implement, which is great. We're not talking like a 2-3 month implementation. It could be a month, and people could already be seeing some new insights on their research. And we have an exciting future ahead. So what I was going to do is, instead of me going through and trying to recap things, I also have a quick video that kind of recaps what I've been working. Okay. I'll stop this. All righty. So that is kind of wraps up what I had prepared. I'm happy to answer any questions that I can from anybody who has been listening. And